This is Larry Benko, call sign W0QE, and welcome back to another video. Or if you're here for the first time, welcome to this channel. Today's topic is about RF power splitters, dividers, combiners, couplers, and samplers. An RF power splitter or divider, which are almost exactly the same thing, take a single RF input and split it or divide it to several ports. An RF power combiner takes several different RF inputs and combines them to one output. An RF directional coupler takes a RF signal in a circuit in one direction only and outputs a sample of that to a port. An RF sampler does not care about the directionality of the signal and just outputs it to a port. So what's common to the above three types of circuits? And the answer is they all have three or more ports involved. Three or more ports usually is something you cannot analyze in a Smith chart program. And up until recently, SimSmith had limited capability in this regard. SimSmith had no capability to analyze anything with three or more ports until the advent of the N block and the ruse block. Actually, it had some limited capability with the F block. But in those cases, you still were limited to one input, but you could have more than one output. As of version 14.9, SimSmith has the ability to have multiple inputs now. So we can analyze these types of circuits, although there are some caveats to doing so. Before we do that, though, let's continue on with what types of circuits they really exist. A power splitter or combiner can be designed to have two ports to combine, 4, 3, 6, 8, several numbers. Usually 2 is the most common probably. 3, 4, 6, and 8 are the next most common. When you get to a certain number like 8, and usually there's diminishing returns and you don't do any more than that. They can be equal or unequal, those ports. You can split a signal into two equal signals, but you can also split a signal into a signal that's twice as big as another signal. And that's done quite often in the case of like a directional coupler. You don't want to take very much of the energy to couple output to the port that's the coupling port that's used to monitor the signal. So in that case, you might only look at 1% or even 0.1% of the signal. In phase or out of phase. The topology of some power combiners is such that the inputs are expected to be in phase, and others the inputs are expected to be out of phase. Some circuits can be operated as either based on which ports you treat as inputs and which ports you treat as outputs. It's all dependent on the hardware involved in the combiner. Isolation or not. Some cases the ports are isolated from each other and some are not. So in the case of a combiner, I have two generators being combined to one output signal. If I lose one of my generators, what happens to the signal? If my load goes away, does my one generator go to the two generators connected together? That might not be good. Some circuits have isolation, some do not. Lumped transmission or lumped or transmission line components. At lower frequencies, we build typically these circuits with lumped components, L's and C's. You can build them with R's in a lot of cases too, with resistors. At higher frequencies, they become transmission lines primarily, and at very high frequencies, they become waveguide components. Nevertheless, the circuits can be built with active or passive components also. This discussion will only concern circuits built with passive components. Many times, like a video amplifier that takes a video input and outputs it to, say, a dozen different devices, will have active amplifiers to drive all the devices. That's not the type of circuit we're talking about today. If you're looking for more information on these types of circuits, there are 3 websites listed. Microwaves 101 has probably 50 or 100 different power combiner circuits that you wouldn't even recognize are power combiners. There are a lot of very specific ones, very interesting ones, built around different impedance transmission lines, built around different lengths of transmission lines, etc., etc. Wikipedia, of course, is always a good source for this type of information. Just go to Wikipedia and then type in RF power combiner or something like that, and you'll come up with lots of information. RF Cafe is another place that's pretty good for lots of different circuits. Again, search for types of names like Wilkinson, Magic T, Branch Line, Rat Race, and you'll come up with lots of information. So what can we do in SimSmith to allow us to look at 3 or more ports? Looking at a blank SimSmith window, we see 2 things. We see a generator and a load. We can put a lot of stuff in between the generator and the load, but even if we do, this group of 3 components looks like a 2-port device. One port is here, one port is here. Nothing else. So how can we get a 3rd port or a 4th port? If we go and we put a ruse block in here, we are capable of terminating the source here internally in the ruse block. And we can do that pretty simply by doing something as simple as this. Put a resistor in series with the source here. And if you're not familiar with how to edit in a ruse block, basically right-clicking the mouse button disconnects the point, and left-clicking connects it. If I want to stop it, I just left-click again, or I can hit spacebar. But if we take this port here and send it on to the load, and then we have another resistor here, we want to call this an output also. So R3 is an output, and this is an output. We now have a 3-port device. One port here is an input port, an output port, an output port. And this is how we build more than a 2-port device. Now this has been around since the advent of the N block, and then later the ruse block. The ruse block, as I've said before, is nothing more than a glorified N block. The ruse block is done primarily for your visual enjoyment. It provides you nothing that an N block does provide. Matter of fact, it gets converted to an N block inside of SimSmith, but it does give you the ability to look at it from a circuit point of view, which is really nice. So this is a 3-port device. So without building up a more complicated device, let me load a circuit here real quickly. And here are two resistive splitters. One's done as a Y with 3 16.6 ohm resistors. Here's a load. I'm calling that load number 2. And the other load here is on the output. And here's another one. Oops. This is a delta version. 50 ohm resistors all around. And instead of having the resistors in series with the ports, you drive the vertices between 2 resistors. Both of them work exactly the same. These 2 have exactly the same equivalent circuit. If you look at that, this is a delta and this is a Y version of exactly the same equivalence. So we really don't need both of them. So let's just get rid of one here just for grins. And let's look at this circuit for a moment. If we go over here, and since I got rid of that one, this doesn't make any sense anymore. What I have is I have the ability to plot the power at this point, and I have the ability to plot the power right here. And the ability to plot the power here, or here, is built in. It's L. So I can click on L, and I see I get a 1/4 watt out. I'm putting 1 watt into this circuit, 50 ohm circuit. I'm getting a 1/4 watt out of it. Over here, I have the ability to manually control a power output plot. I'm saying this is what I'm going to call its name. I'm going to look at U1, resistor 4, the power across the resistor, or power through the resistor, and I'm going to plot it on the power axis, which is this axis right here, the standard power axis. So when I click on this, the line turns blue. What I basically am saying is that output is a 1/4 watt, that output is a 1/4 watt. So I put 1 watt in, I divide it equally between 2 ports, each a 1/4 watt. Not very efficient. If this was an efficient circuit, I would get a 1/2 watt out on both ports. However, I lose a 1/2 watt inside this splitter. That's okay. The resistive splitter is a very nice circuit. It's very flat with frequency, and it goes all the way down to DC. So it's a circuit you can actually buy, and it's quite useful. It has very little isolation between the ports, but that's the way it goes. Let's look at it from a little bit different point of view. What happens to my circuit? And by the way, the SWR here, which is shown with G right now, is 1:1. What happens if one of these circuits is not 50 ohms? What if this is 25 ohms? What happens to my SWR? It rises to less than 1.2. What if this one is 25 ohms also. It rises again. So the input SWR you see is a function of these two load resistor values. We can vary them all over the place if we want. We can, you know, it doesn't matter what they are. Is it possible to come up with some other resistive value that gets us a very low SWR? And the answer to that is yes. These two, neither one of these are 50 ohms, yet our SWR is almost 1-to-1. However, if we look at the power in both of those devices, both the output ports, the power in the load port is now 0.3 watts, and the power in the port here in the ruse block is 0.183 watts. So it's not equal power splitting anymore if the loads aren't equal resistor values. But nevertheless, this gives us a way to have a 3-port device analyzed in SimSmith. Now, while we're doing this, you might say, well, that's really nice, but that only works for power splitters. What about power combiners? So what can we do? A power combiner, we really want to have 2 generators and 1 load. And you might say, well, a circuit like this is symmetrical. It could be used as a power splitter or a power combiner, and you're absolutely correct. But the way I look at it when it's a power combiner is a little bit different. I need to be concerned about things like one generator interfering with the other generator in case of load impedances being incorrect. I might want to look at it look at it differently. Even though it's an equivalent circuit that's doing it, I look at it differently. So it'd be really nice to be able to generate 2 signals that we put into 1 load. So can we do that in SimSmith? And the answer is yes. I just brought up a new circuit here. And this circuit has a voltage-controlled voltage source within it. When you bring up your ruse block and your version of SimSmith, you may not see this component here. This component is an optional component. There are 2 optional components. They are controlled right here with feature key. If you put VCVS in here, or I'll put another one in here, VCCS, voltage controlled current source, voltage controlled voltage source. Then I'm going to close this off. I'm done. Bring it back up again. Now I have 2 circuits, a voltage controlled current source and voltage controlled voltage source. These voltage controlled sources, and by the way, there's 2 of them. There's also 2 more. There's current controlled voltage source and a current controlled current source. They do not have a component in the ruse block at the moment. I don't know if they ever will or not. They can be specified in the text field here. You can basically say I want a voltage controlled voltage source between, and I have to label all these points here, and then I say my device, which won't show in the circuit, is between these points. That's really a little bit out of the realm of this discussion right now for the moment, but you can do it, and it's described in the N block under the I think under the controlled sources. I think it's controlled sources. Let's just find it right now. There they are, controlled sources. These text fields you would put in the ruse block right here, just as you'd put them in the N block, and you can create the generator here. But what we've built here is a generator. So what we've got is we got a 50 ohm load, 50 ohm source here, generator, 50 ohm output impedance. We have a 50 ohm load here, so we get the correct voltage right here. We have a generator that takes this voltage here, does not draw any current. It's high infinite input impedance. It's a mathematical symbol only. It's got a gain of 2, a new 50 ohm load resistor here, or load resistor in series with the generator, and then an output. So if we look at this circuit, what we see is, let's plot the waveforms here. I went through this construct and the harmonic video I did, but fundamentally SimSmith has a wave command. It's kind of interesting. It's plotted on a square chart, and it's really kind of weird in that when you plot it, you don't get what you really think you're getting. So let's plot it and see what we get here. We always get 2 cycles of the waveform, no matter what the axis is or anything else. It doesn't matter. We always get 2 cycles. This axis here was set. Well, the frequencies up here. I mean, now it's set to megahertz. It doesn't matter. It doesn't do anything different. Forget the time base here. The voltage scale works. So For a 1 watt source, you would expect to see 7.07 volts across 50 ohms. 7.07 squared divided by 50 is 1 watt. We see a 10 volt peak signal. 10 volt peak sine wave signal, let me make it a little bit bigger here. 10 volt peak sine wave signal is indeed a 7.07 volt RMS signal. This is the correct signal. So that's what we see right here at this point. We'd expect to see that right here. Over here at W1, we see exactly the same signal. So we have created a signal here that looks just like what we started at the beginning. However, we could replicate this circuit in here to be 2, 3, 4, 5, 6, 7, 8 generators if we wish. And let me load a program that shows a couple generators. Now we have 2 generators. And again, it's the same circuit as before. We only needed 150 ohm terminating resistor for the initial source out here. Both of these generators take the voltage right here and look at it. These labels can be anything. They come into the circuit always as if they were ground, but you can rename them. You can rename them at will. This is one of the things that was added to SimSmith that I thought really improved the ruse block. The ruse block is kind of a, think of it as a schematic editor where you have control over where you place the components, but you have no control over where the wires are placed. And it does that on its own, of its own volition as it wishes to. And sometimes the lines go through other components and stuff. And if you want to control that so that the circuit looks a little more tidy, you can create points which are they're like labels. So label W0 here connects to W0. It can also be used in a plot command or anything else, but they connect together. So there's effectively a line here to here. And in this case right here with the 2 generators, we can see, let me turn everything off here. The initial waveform is 10 volt peak to peak, 10 volt peak to peak signal, 10 volt peak signal, 20 volts peak to peak. That's our 7 volt RMS signal. At point W1 here, we see another signal, same size exactly, 50 ohm load on the output. At W2, we see another point, exactly the same magnitude with 50 ohm load here. If we were to change this load resistor here or this load resistor here, we would see that the other one doesn't change. So let's change the load resistor on the output. We start to see the load here voltage change. This one does not change at all because back here, this voltage hasn't changed. These monitor the voltage, very high impedance. They create a new voltage source, and they're independent. So these are 2 independent generators that have nothing to do with each other. So now, is this good enough to do a power combiner circuit? The answer to that is really not quite yet. So let's load another circuit here. And we're getting closer here all the time. This circuit. I've got three circuits in here now. Three voltage controlled voltage sources. And if we look at this, there's no resistor here because this one down at the bottom has created a delay with a piece of transmission line. Ignore that for a minute, but this 50 ohms gets transferred across to here, and there's 50 ohms right here. So the first generator is our standard generator with value of 2. Our second generator, though, has a different value. It's got a complex gain. And that complex gain is written here. Let's move this out of the way a little bit. Such that I can make the signals. Let's get rid of everything here. Now, here's the original signal that comes in, and I want my second generator to, if I'm going to build a power combiner, I'd like to be able to vary the difference between the 2 input signals, both in magnitude and in phase, so that I'm capable of seeing the effects that the power combiner has when the signals are not identical. So what I've done here is I've got a parameter I can set 2, which is the magnitude of the gain, and here's the phase I want of the signal. So if I plot the second signal here, which is at W2, well, W0 is here. If I plot W1, W1 is the same as W2, of course, like it was before. Here's W2. It's moved over, and I can change its phase. I can change its magnitude, and I can do it at will. So this now gives me the ability to be able to do anything I want in terms of the two signals that I could put into my power combiner. Now, while we're at that topic, I might mention something here that's a little bit, it's an important point, but maybe it isn't as important as you might think. If I change the frequency here, these two waveforms will maintain the same phase relationship. If I was to generate my out-of-phase signal with a piece of transmission line, they would maintain a time relationship. So let's plot W3 here just for grins. Right now, this piece of transmission line was set to be 12.3 feet in length, velocity factor of 1, which meant this was a 45-degree phase shift at 10 megahertz. And that's a constant time delay through this piece of transmission line. So if I go to 11 megahertz here, look what happens. 12, 13, 14. I see the phase relationship between the primary signal and between voltage control generator 1, voltage control generator number 2 remain the same in degrees, but this to here is the same amount of delay in time. So if you had two signals you wanted to control that were offset by a certain number of milliseconds, you can't use this construct anymore. You have to put a delay line in there. Either one of these ways to do this is equally good. They both work the same way. Generally, when you're doing a circuit, you expect the two input signals to be identical in a power combiner. You expect the phase to be either 0 degrees or 90 or 180 or whatever it needs to be for that type of power combiner, and you don't worry about it. But when you're trying to understand how the power combiner works, it's nice to be able to vary them in smaller increments and see what the effect of those circuits are. And you look closely down here. I generated them this way. It's pretty straightforward. I've done this before, I think in a couple other videos for some other functions I needed. But fundamentally, the cosine of the angle I want in radians. So this is degrees times pi over 180 gives me radians. So the cosine of the angle is the real part of the gain, and the imaginary part of the gain is sine of the angle in radians again. So all these files will be available to download, and you can play with them at your heart's content to see the difference. But this little difference I thought was worth at least mentioning. There's one more thing we need to do before we can finish up and begin our analysis of a real power combiner. And that is, we need to be able to measure the impedance as seen by both of the generators due to the load. We want to measure the impedance here, we want to measure the impedance here, or here, whatever it would be on our generators when there's a circuit out here that's a power combiner. So how can we measure impedance? Well, SimSmith measures impedance pretty nicely between blocks. We can measure the impedance at this point, but within the circuit, can we measure the impedance? And that becomes the last piece that we need to be able to figure out how to do. Okay, so here's another circuit. And this circuit is done just solely for the purpose of trying to calculate impedance. I've got two circuits that are identical. This circuit, I know what it really is. This circuit, I know what it really is, and they're equal circuits. They're 50 ohms in parallel with 318 picofarads. What I'm going to do here is with two resistors, and if you notice closely, the dot on the two resistors, the phase dot is different. The phase dot is a SimSmith convention, like it is in a lot of programs, as to which way the current is flowing in a component. What we can do in SimSmith is we can plot, get this a little bit out of the way, we can plot the voltage, in this case, U1W1.V, which is the voltage right here at this point. We can plot this voltage divided by the current going into this resistor R1. Now, if that's done properly, we'll get the right value. If it's done wrong, we will get a negative resistance, and we'll be outside the Smith chart. So we have to figure out which one of these circuits is the right way to do it. Now, can we look at the voltage on both sides of the resistor and do it? In my case, the voltage on both sides of the resistor here is about equal because I've got 1 micro ohm of resistance put in there. But what if this resistor was a larger value of resistor, 50 ohms, say? Could I still do the calculation? What about when the polarity is this way? So let's look at these a little bit more closely. So we know what the circuit really looks like. It looks like the impedance right there. That's the swept impedance of the 318 ohm in parallel with, whoops. How about now? 318 ohms in parallel with 50 picofarads, with 318 picofarads in parallel with 50 ohms is this plot right here as we sweep from frequency from 1 to 100 megahertz. Now let's see what we measure by doing this one. Now, we can't see anything because it's right on top of it. So this calculation works fine. The polarity of the resistor is appropriate. Let's see if this one works okay. It works just fine too. Both of those work fine. The polarity is correct. Both of these, I suspect, are, yep, that one's outside the Smith chart, and that one's outside the Smith chart too. So these bottom two do not work. We need the polarity of the resistor to be right here in order to have this work appropriately. And that's pretty easy to do. What if this is a 50 ohm resistor instead here? If it's 50 ohms, we would expect to see the resistance here, measured here, to be different than here by the 50 ohms. So let's see what we get. Turn these back off. Let's look at the one from W1 here. And we see that from W2 we see that. Looks pretty good. Let's see if that's really, really correct though. So what we're going to do here is let's get rid of the capacitor here. Let's get rid of this capacitor down here. I won't get rid of it. I'll just delete the trace. And now what I see is the impedance I see when the calculation is done from here is 50 ohms. The impedance I see when the calculation is done from here is 100 ohms. So it doesn't matter what the resistor value is here. We just need to get the polarity right relative to measuring the voltage. This is the last piece of the puzzle needed in order to get SimSmith to be able to analyze power combiners. I will do this in the next video as this video is running a little bit long. Hope this has been interesting, and I would appreciate any comments that anyone has. Thank you.